Here's a question for you. Do you recognize chemistry when you see it? It's an interesting thought, really. I mean, it's pretty basic and straightforward, but actually it's a little bit subtle too. It's sort of like asking the question, do you recognize happiness when you see it? I mean, you could say, yeah, because you can tell maybe a person is laughing or they're smiling, and there's certain outward things that you could look at. But to truly understand whether a person is happy, you'd have to kind of get inside their head and recognize what's going on inside of them to really know whether or not that person is truly happy. And chemistry is kind of the same way. Turns out that we really can't see exactly how atoms are moving, so we try to make models and inferences about what the atoms are doing. And so in order to understand whether what you're looking at is a chemical process or not, you have to kind of picture the atoms and molecules and what they're doing. And so we need to spend a little bit of time thinking about that. And once again, I'm going to ask you to do a conceptual drawing, and hopefully by kind of envisioning things at the atomic level, it'll help you to make those distinctions. In this case, we're going to be looking at the distinction between what's classified as a chemical change and what's classified as a physical change. So on this page right here, we're going to look at two examples of physical changes, and these were physical changes that we saw in class. The first demonstration that I did for you was we took a pre-1982 penny, which you recall is made up of pure copper, or almost pure copper, and we heated this up to the point of incandescence, which means it emits light. So how do we picture copper atoms? Well, I've tried to draw that on the left-hand side, and you got to remember that this is just the beginning of the class, so this picture isn't perfect, and we're going to change it as the year progresses. But for now, it's not a bad model for how we picture atoms. Basically, they're little spheres. If they're in a solid, they're pretty close together, and those are things that I've tried to show in this diagram. Another thing to think about is whether or not they move. Well, scientists think that atoms are constantly in motion, and in fact they never ever really slow down to no motion at all, or that they're not moving, unless they're at a very, very cold temperature, which is called absolute zero. But at room temperature, they're certainly moving. But atoms in a solid are sort of constrained. They can only move in one kind of way. They can just basically bump into each other. And as they bump into each other, they knock into the neighboring atom, and that starts them vibrating. And the next thing you know, the whole of the material is vibrating more or less at the same speed. Using this model of the motion of atoms, we can imagine how metals are good conductors of heat. So if we put a copper penny into the flame of a propane torch, those atoms are just thought to start to move faster and faster and faster. So after we've heated it, the only thing that's really changed is that the atoms are moving faster. And if we cooled it back down, the atoms would slow down. There are some changes that might occur, like it might spread out a little bit, it might expand by a tiny amount, but on the whole, basically, these atoms have remained the same, and if we cooled it back down, if we reverse the process, the material basically is unchanged. And so this is an example of a physical change. Now, how a hot object emits light turns out to be really a fascinating and interesting question, and something that we'll look at later. But for now, you can just imagine that vibrating atoms oscillate, and they create waves of light, and those waves of light reach our eyes, and that's what we call incandescence. Again, that's a pretty simplistic kind of look at it, and later we'll look at that in far more detail. Okay. The next thing we did is we took a piece of zinc and we heated that up in a propane torch, and we found that the zinc melted. So let's try to get a picture of what happens when something melts. So in my diagram here, I've drawn some solid zinc atoms, and I'm kind of spreading them out a little bit more than the copper, because we remember that zinc is a little less dense than copper. Now, in a liquid state, one of the major differences is that these liquids, or atoms in a liquid, conform to the shape of the container that they're in. Now, so what happens between being converted from a solid into a liquid? Again, we can imagine the atoms and how they move, and zinc at room temperature would not look all that different from copper at the same temperature. The atoms are vibrating, and that's about all they can do. But as you heat this up, the atoms move faster and faster, and they weaken the bonds between the atoms. And the atoms gain a different type of motion. They can begin to roll. They can also vibrate, but they've gained this ability to sort of flow and roll. And so a good model for imagining a liquid is to think about, for example, marbles, so loose marbles in a bowl or something like that. And with this sort of picture of a liquid state, we can kind of understand some of the properties of liquids as well. But again, here the zinc atoms remain zinc atoms. And so this is a physical change. Alright, so now let's consider a couple of chemical changes. And again, we're going to look at a couple of demonstrations that we did in class, and we'll use those to illustrate some of these principles. In chemical changes, these substances are actually changed, and you usually see some kind of dramatic change in the actual appearance of the material, and sometimes a release of energy and other things too. But you have to imagine what is going on, and the key to understanding a chemical change is that either some bonds are broken or some bonds are formed. And again, bonds are something that we're going to study later, but my guess is that you've probably heard about these, and you might remember there's two types of bonds. There are ionic bonds and covalent bonds, and again, that's getting ahead of the game, but basically when a bond happens, the atoms stick together and they are connected by what we call a bond. And as I said, we will get into that in great detail later. But let's just take a look at the picture on the left. Imagine the zinc atoms, which are shown in gray, and the surrounding air contains some oxygen. The oxygen atoms are gaseous, and they are moving at far greater speeds than solids and liquids. They slam into the zinc and bounce away, but every now and then they will slam into the zinc atoms, and at times they will actually connect and stay stuck to each other. This is what we mean by a chemical bond. We illustrate a chemical bond by sort of showing the two atoms, which are drawn in circles, kind of overlapping each other. And so in my diagram, I've shown two compounds that are formed by the combination of zinc and oxygen. And that was, if you recall, is called zinc oxide. It's a whitish powder material that lifeguards sometimes put on their noses to help to reflect the sun and so forth. So that's how we illustrate a chemical process or chemical change. Alright, the last one was kind of tricky. In this case, we took some sulfur, which was in a solid state, and it was brittle, and we heated it till it melted, and if you recall, it changed color, and I poured it quickly into water. This created a strand that sort of looked like taffy, and if you pulled on it, it sort of was stretchy. Sometimes that's called rubberized sulfur. So I'm trying to draw kind of an illustration of that. Again, please remember that these aren't totally accurate pictures, but at this point we're just trying to represent some things that are going on. And in this case, we need to understand a little bit about how chemists symbolize things. First of all, you'll notice that we use the letter S to represent the element sulfur. And in this case, we're asked to draw some S4, sulfur. What that means is that there are four sulfur atoms that are bonded, chemically bonded to each other. And in this case, I've drawn a total of 12 atoms that are each bonded together in clumps of 4. Now, when these are heated, they turn into rubberized sulfur. And here we're being asked to draw one S12, I guess you could call it, a molecule. And so that would be 12 sulfur atoms bonded to each other in kind of a long noodle-ish shape. Now, when that happens, you can kind of imagine that this would be able to be pulled and squished, and it would be far less likely to break, as if you looked at the diagram on the left. That would be something that could more easily break apart than the rubberized sulfur. But if you look at this picture and think about it, the question that you need to ask yourself is, again, are bonds being broken or are bonds being formed? And that's when a chemical process happens. And this is, again, tough because a lot of times, you don't know or have the background to know whether or not that's happening. But the key to it usually is to try to ask yourself, was there some really dramatic change in properties? Because usually dramatic changes in properties are associated with some kind of chemical change and not a physical change. So I know this is probably still not crystal clear, but hopefully that helps. And if you keep on working on trying to imagine what's going on here at the atomic level, I promise you in the end it'll all begin to make sense. So hope you enjoyed that little video.